the opportunity. My name is Ariane Soret. I work at Candela in the theory team. And I'm going to talk about work that we did in the previous year, where we analyzed the energy consumption of a task called boson sampling and showed the existence of a quantum energy advantage regime. So this work is done in collaboration with all of these people. Nassim was an intern at Candela, and the others are permanent employees at the company. The people most involved in the project were Pierre-Emmanuel Emerio, who is in the algorithms team. And I should mention that this project is done within the OECQ consortium, which stands for Optimization of the Energy Consumption of Quantum Circuits. It's a 4-year project which aims at optimizing specifically the energy consumption of photonic quantum computers together with Alice and Bob, EDF, and the CNRS. So before diving into the core of the talk, I want to give you just a little overview of the company and what is our technology. So Candela is a spin-off of the CNRS created in 2017. And initially, the company was producing single photon sources. Today, we produce photonic quantum computers to do what is called discrete variable quantum computing, because the way the computers operate is we use single photons to encode the information and carry the information. The approach is full stack in the sense that we build the some enabling technologies, such as the single photon source and other pieces of equipment, all the way to the QPU. And we also develop softwares and algorithms to make the devices accessible via cloud. So the building block of the technology is the single photon source here. It's a semiconductor quantum dot-based single photon source. So the idea is we have a quantum dot here embedded in a semiconductor, specifically indium gallium arsenide, which is then put inside a cavity. And then this source is able to produce on demand identical photons of high purity and high indistinguishability. So we have a laser that would excite the quantum dot, and then single photons are emitted. With that, we can do quantum computing. Specifically, what happens, like the way the schematic representation of how the quantum processing unit operates is we have our source here, which is put at a cryostat at 4K, which produces streams of identical photons. And then these photons are sent into a demultiplexer where they are aligned before they enter an interferometer, which is at room temperature. So this interferometer consists of linear optic components, beam splitters, and phase shifters, and is able to encode any unitary you would like. After the exit, the photons are detected by superconducting nanowire single photon detectors at cryogenic temperatures, and the results are interpreted. And then the user can send instructions to reconfigure the chip, and so on. So this is for the overview. In a few numbers, so I mentioned the elements that are cryogenic temperatures are the source and detectors, are 4K. Here is a picture of the first QPU that was online, which had 6 photons. Currently, we have one of 12 photons, 24 modes, which is online. And in terms of gate fidelity, we've achieved these number here. And you can find all of the details in the paper mentioned there. So we're at the QEI conference. The topic is energy, so I've highlighted the power consumption of the device, which is currently at 3K. So it's a relatively low power consumption, but as it's been also mentioned in the previous talks, the device is also itself quite small. So maybe it's not so amazing to have a low power consumption. The interesting question is, how does that trend change as we will scale up? So this is the question I want to start to address in this talk. I will not talk about fault-tolerant regime, so very large scale. We will stay in the NISQ regime, so nearly intermediate, noisy intermediate scale quantum computing. But the point is to present to you a framework and like a model that we've put together in order to analyze and optimize the energy consumption of the device. And that model will serve as a first building block as we go forward and increase the size of our devices and go towards fault tolerance and error correction. So the outline is the following. I will present to you, so in terms of method, we've used the metric resource noise methodology that has been discussed many times already in the conference, adapted it to photonics. I will present that, then I will talk about the use case we've chosen for our analysis, which is called boson sampling, and finally get to the results. As we've mentioned already in the talk, in the conference, the MNR methodology was introduced in this paper by Marco Felusasiani and collaborators, and it's a general methodology to modelize and optimize the energy consumption of quantum computers. In the case of photonics, so I'm going to explain how it works in the case of photonics. For a recap, the idea of the methodology is you want to identify control parameters that control every element of in these boxes. So the performance is a metric that is decided by the user and is, let's say, task dependent. Noise is any element of noise that can block, or let's say can make hard to achieve a high performance metric, and then the resources is whatever resources you need to spend in order to achieve the performance. In this talk, I will really focus on power consumption and energy as a resource. And for that case, what we identified as the relevant control parameters are these two values, the photon number, so that's how many photons you put in your device, and the cryogenic temperature, T. Now let's open the boxes of what we have exactly in the noise and the resource sections. For the performance, I will talk about that later when I introduce boson sampling. The main source of noise we have in photonic quantum computing is photon loss. It occurs over the whole circuit, mainly at the interface between the chip and the fibers. And the issue is that it scales, it has a terrible scaling with the size of the problem. The end-to-end transmission basically follows an exponential decay law with the number of optical components you have. Notice that earlier I said that we would like the noise and everything to depend on these two parameters, and here I have an expression for the transmission that depends on the number of optical components. It will be important later I will show you later how to relate that to the number of photons, but that will be specific to boson sampling. Second source of noise is the distinguishability. So it's important that the photons emitted by the source are indistinguishable so that you can use quantum interference effects to get a quantum advantage in the computation. However, because of interactions with the phonon bath and the environment in the semiconductor, the photons tend to become distinguishable, lose, let's say, indistinguishability. And what is nice is that we have an explicit formula relating the indistinguishability of the photons to the temperature of the bath, which was derived in that reference here. Do not try to understand I'm not going to detail the elements that are in this formula. What is important is that the distinguishability, so which is defined as 1 minus the indistinguishability, depends on the temperature of the cryostat. And here you have experimental data points confirming this analytical curve. Small caveat at this point, this is a good formula for single source indistinguishability. When you have multiple sources, additional sources of noise need to be taken into account. It's ongoing work because it's a difficult task, but for now this is a good assumption. So that's for the noise. Now let me talk about the resources. We're going to focus on power resources, and in the current devices, about half of the resources is taken by cryogenics, and the rest is for all of the rest, basically. I apologize for the ugly little box here. The cryogenic devices we use are relatively small cryocoolers, so such as these McMahon cryocoolers, in which we put the sources and the detectors. A simple formula to evaluate the power consumption of the cryogenics is given here. Essentially, there's a finite number of detectors you can put in the cryostat. This is in this ND per cryo. So what this value in parentheses counts is simply the number of cryostats you need. If you know that you need ND detectors and you can only put a finite number in a cryostat, you might need more cryostats. And then the prefactor here, you have P0, which is the cooling power. So that's the number of the amount of cold that you extract at low temperature. For instance, for the specific example of the hardware we use at Condela, to give you orders of magnitude, we have a cooling power at 50 milliwatt at 2.5 Kelvin. Then you divide that value by the efficiency, which is computed as a fraction to the Carnot efficiency. In our case, 0.4% of the Carnot efficiency. And what is nice is that, again, you have an expression for the power consumption, which depends on the temperature of the cryostat through the Carnot efficiency. So we have related this resource to our control parameters. Other resources involve many things: the laser, the control electronics, all the classical overhead for encoding, decoding, compilation. I will not optimize that. It is going to be counted as a fixed cost that we set to 1.5K due to what we measured in the lab. Now, so this is for the noise and resources part for the device. Now, to define the performance metric, as I said, it's task dependent, so let's describe the task we're going to look at. So boson sampling, I'm assuming many of you never heard of it before because it's whatever. Boson sampling is very simply put, the task is the following. Assume you take a universal interferometer, you take an input of n single photons, you detect the output, and you get, you repeat that many times, you get many samples, and these samples follow some probability distribution. The task is to produce is to sample from the output of such a distribution. So, as you can see, it's completely native to photonic quantum computers. But the point is, if you ask a classical computer to to reproduce the same statistics, it becomes exponentially hard. Because in order to get the output statistics, what you need to do, classically, is to compute the permanence of a submatrix of the unitary that is encoded in the chip. A permanent is like a determinant with only plus signs, and this is extremely hard for classical hardware. It scales more than exponentially with the size of your sample. So this task was actually designed to showcase a computational advantage in photonic quantum computing. You can find the details in this reference here by Ariane Soret and Arkhipov. So since it's a historical task for showcasing computational advantage, we thought it was pretty natural to re-examine this task from an energetic perspective and see whether we would have also some energetic advantage in this same task. Technical detail, but which actually has an importance for realistic implementations of boson sampling. Initially, complexity proofs were done in the so-called collision-free regime. That means you assume that all the photons exit in different detectors. This happens when you have many more detectors than photons, specifically when the number of detectors scales like the square of the number of input photons. The issue is that then you need extremely large chips, which is hard to create, and especially because of loss. But recently, there are proofs of complexity that show that you also have an advantage in the linear regimes. Specifically, the moment the number of modes is larger than twice the number of photons, you have a computational advantage. So we're going to choose this limit because it drastically reduces the hardware requirements. Okay, so now how do we define a performance metric in boson sampling? A natural choice would be to take the size of the sample, so how many input photons you put. The issue is that in practice, as I said, there is noise, so you would have photons that are lost, photons that become distinguishable, so you need a metric that accounts for these imperfections. And thankfully, the answer was given to us on a silver platter by Renema et al. And co-authors in this reference. What they did is to consider a boson sampling task where you have noisy photons because of loss and distinguishability. And they showed that you can compute this value k. Do not try to understand the rationale behind this, but what's important is they derive this value k, this number k, which depends on our control parameters, input photons, temperature of the cryostat. And what this represents is the number of perfect photons that make the task hard for the classical computers. So specifically, imagine you input m photons. Some of them are going to be imperfect. The task of boson sampling then becomes equivalent to having a task of boson sampling with k perfect photons. So that is the part that is really hard for classical computer, and the rest is easy. So basically, k is a good performance metric because it tells you how hard the task is for the classical computer. Minor adjustments. This was again derived in the collision-free regime, but it's straightforward to adapt it to the linear regime. I'm not going to go into the details. So the key point is that now we have all of our complete picture to apply the MNR framework to boson sampling. We have a metric which depends on our control parameters. We have a constraint on the number, we have a relation between the number of modes and the number of detectors, which allows us to now express our resources and the noise completely in terms of these two control parameters that we identified at the beginning, the number of photons and the cryogenic temperature. Now, to give an intuition of what is the trade-off we expect, imagine that we want to increase the metric, the performance metric of our problem by spending the same power resource. So to increase the metric, we need to increase the number of photons. That means we need to increase the number of modes and detectors. With more detectors, you would need at some point more cryostats. So if you want to keep the same power, you need to operate at higher temperature to save on energy. If you are at higher temperature, you have more distinguishability, which reduces the quality of the photons and lowers the metric. So you have this trade-off. So we expect to have to find nice optimization points. Okay, so now I get to the core of the results, essentially, of the analysis. To do a complete analysis, we wanted to compare, so to look at the energy consumption to make a sample in boson sampling, and also the time it takes, and have a time and energy comparison between quantum and classical. So we need to fill this box, energy per sample and time per sample for classical and quantum. To get the classical information, what we did is to use an algorithm that was defined by Renema and co-authors, which evaluates the number of floating point operations a classical computer needs to do in order to compute, to perform the boson sampling task, given this performance metric M. So we have this value L, the number of flops. Then, to get the energy consumption, we looked at what is the most energy efficient device that we have currently available from the Green 500 data list. And the device at the time when we looked it up had an efficiency of 72 gigaflops per watt. So with that, we have our formula for the classical energy consumption. For the time consumption, for the time spent, it's the same idea. We have this same number L of flops, which with this time divide by the number of flops per second the device is able to do. On the quantum side, the energy per sample is simply given by the product between the power of the device and the time it takes to produce a sample. The time to produce a sample is expressed as the inverse of this rate, which depends on how many photons you want to produce, the rate of a single photon source, and how many sources you need. And finally, the time per sample is simply the 1 over the rate. So with all these elements, we can now do our analysis, and what we plotted is, what you see here is a comparison between the energy of for the quantum side, which is the colored bar, and the classical cost, plotted against the metric. So that's the number of idealized photons. And here as a color bar, you have the requirement on the transmission efficiency that the quantum computer needs to have. And on the right-hand side, we did the analysis for time. So what's interesting here is that you see that the threshold for quantum advantage, meaning when the quantum computer performs the task with lower energy than the classical computer, happens before the onset of the computational advantage. Which means that you have this gray area here, which is a pure energy advantage area, where the quantum computer is slower than the classical computer, but operates at lower energy consumption. How much time do I have left? Okay, good. All right. So that's when we found out, we were happy to find that we have such a regime of quantum energy advantage. One thing that is put under the rug is that here the number of lost photons is assumed to be fixed. So we fix an arbitrary number of lost photons and we do the analysis. In practice, in the lab, when you have a device, it has a given transmission efficiency, and when you do your experiment, the number of photons that go through follow a binomial distribution. So you never have a fixed number of photons. This never happens. We wanted to take into account these fluctuations, and we did the following. For every point that we had in our initial analysis, we extracted the requirement on the transmission efficiency of the device. So at every point, you can compute an end-to-end efficiency as simply the ratio between the transmitted photons and the emitted photons. from this transmission, we computed the, knowing that realistically, if you have a device of a transmission efficiency eta E, the output photons follow binomial distribution, which means that you also have an output metric that fluctuates, following a histogram like that. Then we re-averaged over all the possible outputs for a given target efficiency, and we plotted this new chart here, where this time in the x-axis you have the average number of the metric obtained after averaging of all these outputs. And what we find is that then you can lower the threshold for the quantum energy advantage. The reason for that is that in a realistic experiment, you have what saves you is these all the elements here. So you have these low probability but very high metric samples, which are extremely hard to do classically and which allow you to gain even more advantage with a quantum device. And finally, we asked what would be the loss budget if we wanted to actually reach the quantum energy advantage threshold. And this is the setup we would need to achieve. So adding simply a second source and with a device of end-to-end transmission of 60%, which is much lower than what you would require in FTQC regimes, we could reach the energy advantage threshold. In comparison, the key numbers I want to highlight is if you wanted to reach the computational advantage, you would need instead 3 sources and a higher transmission, which is much harder to achieve. So the one takeaway is that in that case, we found that quantum energy advantage, not only it's separated from the computational advantage one, also the onset is earlier and makes it more reachable experimentally. Maybe I comment on this very quickly, just to visualize, because I think the metric we have for boson sampling is perhaps an abstract number. This here, it's to represent what would happen if you would actually do the experiment. So assume you build your setup, your 51 mode interferometer. When you would use it to do boson sampling, you could increase the number of photons you inject gradually. And here, what you have in this plot is the energy per sample in the quantum and classical case. And you see that the energy per sample in the quantum case is always pretty low because you just spend energy because you run the device longer, but it's not drastic. But here you have in the middle the cost for the classical one that explodes when we reach high metrics. And then what happens in the saturation when we get to higher numbers, the issue there is that you have so much lost photons that you lose the advantage that you had, let's say, in the middle. Okay, so I leave you with the conclusion side. So the takeaway from this talk is we've adapted the MNR technique to photonics. It's a first building block, and we will use that forward for more projects on FTQC and quantum correction. And what we found is that you have an energetic advantage before computational advantage is boson sampling. For more on the topic of photonics, but in the quantum error correction regime, we have Nathan Shatel's talk this afternoon. And yeah, and I added here the references of the 2 main work in the paper. And with that, I thank you for your attention.
Thank you for a very nice talk. Do we have any questions?
Thank you, Ariane, for a very nice talk, really. Many questions. I will just pick one. You compared against classical computing, choosing the most energy efficient computer.
Yep.
What if you choose the most powerful, which I understand it is like 1,000 times more powerful computationally, but the energy efficiency is only a few % less?
I mean, at the end of the day, what is important to us is the energy efficiency, so the energy you spend per floating point operation for the classical hardware. So if you have a more powerful one, I assume then you would be faster, so the classical computer would be faster, but the energy per floating point operation might be the same. So, yeah.
No, but sorry, my question to clarify was, if your classical computer is 1,000 times, to say, more powerful,
yeah,
how would the threshold for the time advantage changed?
Yeah, so the intuition is if it's more powerful, you would be faster, so you would lower the threshold, but probably not change the energy line. So yeah, so I guess your point is if I take another hardware, could I have the onset of the computational advantage faster? Perhaps. Then we would have to see in terms of orders of magnitude because the classical hardware that tends to be the most energy efficient is also a lot of times also in the most powerful efficient, right? So it's
it would make it harder for a quantum
exactly.
harder for the
Yeah.
computer to beat the classical one.
Exactly.
So the energy advantage would stay,
Yeah.
the computational
Yeah.
advantage would disappear.
Exactly. So this line would basically go. Wait. Yeah, because the black line would be moved to the to the right. Yeah. Sorry, it would be further away. Yeah. Yep. So the question is, why do we use SNSPDs versus quantum dust-based detectors? Okay, this is really outside of my field of expertise. I don't know, I'm sorry.
Maybe I have a quick question, if I can. So boson sampling is often treated as a tailored problem for a specific platform to show quantum advantage. However, it feels like these things actually naturally appears in many physical problems. I mean, permanence, right? If I want to estimate high order moments of a Gaussian, or even, for example, I make a weak power expansion in quantum field theories and I want to estimate observables in that regime, I have this expression. So why are they not used rather for quantum simulations? Is there a research around this?
The question is why don't we use boson sampling in?
So maybe it's technical and maybe we can talk later. I don't understand why boson sampling is treated as a fake or a toy model just to show quantum advantage and not as a quantum simulation platform.
So, first of all, there are usage. You can use boson sampling beyond just doing boson sampling. So there are ways to improve Monte Carlo simulation schemes with boson sampling. You can use boson samplers, so the device to implement schemes in quantum machine learning with reservoir computing and so on. So you have all these applications. In terms of the simulations to compute permanence for other fields, this I do not know of, but we could discuss more after.
Okay, thank you.
And quick last, could you just show again the budget, the loss budget there? This is perfect. So how realistic are these numbers for energetic? Yeah, like you would need, especially I see the Mach-Zehnder interferometer coupling needs to be much better.
Yep.
Like, is this something you think is realistic in the near future, or?
It's not crazy, honestly. Also because, I mean, okay, if we really wanted to do that, there would be ways to cheat around. So for instance, this value here for the transmission of the Mach-Zehnder interferometer, which is extremely low, comes from published work where what they did is to design a device that does only boson sampling. It's not a universal chip. So if you wanted to create only a device that does boson sampling, you would build your hardware in such a way that you could reach these numbers. In practice, we also want a chip that does universal computing, so we fall in that second line, and then it's a bit harder, but I don't think it's insane. I don't want to give values in years, but talking with people in my lab there, it's hard, but not completely out there. Yeah.
Okay, so we thank the speaker again.
Thank you.
And